We've seen how we might predict the behavior of a system if we knew all of its physical characteristics. And we could define a second order model if we knew the mass and the damping coefficient and the stiffness of the system. Then we could predict how it would behave. However, if the system has some nonlinearities in it, or if we don't actually know the physical parameters, we'd really like to be able to go the other way and extract a second order model from data we measure with, say, maybe a step function. So the technique that we would follow is we'd apply a step function input to our measurement system in the real world and watch for overshoot. If there's overshoot and decay, if it goes up and oscillates back and forth and damps out after a while, then we know we should be able to get a reasonable approximation from a second order model. And we can take a generic second order model like this. This is the kind of an equation you'd work with in your ordinary differential equations course. So it's got a stiffness coefficient and a damping coefficient that relate to the second derivative of whatever the measured value ym is and relate it back to the input value y. So we'd like to be able to use this kind of a model to extract data or extract information about performance from a step function input to one of our devices. Now, in the real world, we'd go out and actually measure this, and you're going to do this in the lab. In our example here, we want to start off with something we know. So we'll start off by assuming that we know K and C here, and we'll generate a second order response just the same way that we have before. So I'm going to run this code. It sets a bunch of variables initially. Then down here, it sets the new measured value of position equal to the old measured value of position plus the derivative of the measured value of position at the old time times delta t. So this is just advancing an Euler calculation, just like we did in the other calculations. And we should see the same step function response. And it's done the calculation. Now it'll do the calculation because I actually got the right cell. And it's doing the calculation over 100,000 data points, so it will probably take a little while. And there's the result we get. That's the same sort of step function response that we got before. And I've normalized all of the values so that they all vary between 0 magnitude and a magnitude of 1. So we're still seeing the same kind of oscillations that we saw before. First order response to a step function. And that first order response is based on assumed stiffness coefficient and damping coefficient of 1987 and 6.87. Numbers I just picked out of the air. And they're giving oscillations that are some fraction of a second in period. I'm going to save the performance of that one. That's our data. I'm going to save that away in this capital YM measured values array here. And now let's just plot the input and the indicated output. So here we were with an input. Up here, the initial value I chose was 273. And it could be pressure or position or mass or anything that we expect to have our second order response. And you see we start at 273, we overshoot 0, and we go back and forth and back and forth. Now, all of that is stuff that we've done before. We've been able to predict this second order step function response before. Now we've got a second order step function response. And we'd like to figure out what the parameters K and C are from that response. So we're going to start off by guessing. These are guesses that I eventually got to, but let's set both of these equal to 1 to start off with. So I'm going to start by guessing my stiffness and damping parameters. And I'll do a calculation. And then I'll plot it out in comparison to what I measured before, the YM value. So here's the response I'm trying to get. And here's what I got. It's going way too slow. So if I want a higher frequency, I need a higher stiffness. So let's try 20. And if I try 20, well, the green line's going faster now, but it's still not the same frequency. So let's try 200. I'm trying to zero in on the frequency here. That still wasn't enough. Oh, let's try 2500. And the frequency, oh, now the green line is oscillating even faster than the orange line. So I need a lower frequency, and I might drop down to 2000. And that looks pretty close. It may not be exact, but it's pretty close to the right frequency. But the damping isn't right. So now I know that I need to increase the damping for this green line to damp out faster. So let's make that 10 instead. Oh, it's damping out too fast. Let's make it 8. Not quite there yet. Let's make it 7.5. And 7.2, 7.1. That's a pretty good prediction there. I think the green line and the orange line are pretty close to each other. That's certainly close enough for predicting the dynamic response for any purpose I need. So I think I've got some parameters here. I've got k equals 2000 and c equals 7.1. Let's go back up and look. Previously, I set k equal to 1987 and c equal to 6.87. So I came out with 2000 and 7.1. That's really pretty close. And the most important thing is it's close enough that I get the green answer in comparison to the orange answer. And those, in terms of practical properties, are definitely close enough to predict what I'm interested in. So I've been able to now extract these values here. I've got some values for k and c, and the natural frequency is going to be the square root of that capital K in radians per second. So let's check and make sure it matches up. So if I run this, okay, so that should be about 44 radians per second, or 7 hertz. So the period should be about 0.1404 seconds. So going from there down to there and back up again, that looks like about 0.1404 seconds. So my natural frequency is matching up, and that's good. So having got that to work, I can go back and use that K and that C to predict the response to a more complicated transient. So suppose I had a transient that looked like this, and I want to use my K and C values to predict the response to something more complicated. Now I've got a sinusoidal variation at a low frequency plus a sinusoidal variation at a much higher frequency. So you might think of this as being the actual signal and some high frequency noise. I can do exactly the same kind of Euler's method calculation here, where I get the new value equal to the old value plus the derivative of the old value times delta t. And I can plot out the input, that's the quantity that I'm trying to measure, and then the modeled output, and see how our transducer is going to do it following it. And if I run that, there's my blue oscillation. That's the input to the transducer. And I see that my transducer is a little bit slow in following that. It's catching the basic sense of the underlying waveform here, but it's not keeping up very well with the higher frequency waveform, which is up towards or past its natural frequency. So if I wanted to know what the response was going to look like for something like this, I would really need to have a model. To have that model, I would really need to have K and C. I can go back and extract K and C from this step function response by curve fitting to make my modeled response match the actual measured response. And that's the approach that you take in practical application. You would apply a step function to your transducer and watch to see it oscillate like that. Then you would tune your model to make sure it matched up in all important respects. Get the frequency about right, get the decay about right. And in this instance, we started off with a system that was a perfect linear second order system. So we got a really good fit. If you go to real data, your systems are not going to be perfect linear second order systems. So you may not get a perfect fit like this, but you still want to get about the right natural frequency and about the right damping if you're going to use that second order model as an approximate model of what's going on.